Zhi Zhong Li. I first thank to the organizer and the NIT30 to make me have the opportunity to talk here, and my collaborators Andrea and Yuti, my advisor, Honghua and Shenqi, for their kind help. Today's talk will be focused on the single and double subtheorems, which is derived by the principle of symmetry. The talk is based on two papers with my collaborators mentioned before. Now they are now on archive. Okay, so the talk will focus on 3 points. The first is subtheorems are detected by symmetries. Actually, it's the spontaneously broken symmetries. That is, if we have a spontaneously broken symmetries, then we will have a Gaussian boson. And the subtheorems of the Gaussian boson is totally determined by the principle, by the symmetry principle. Okay. And the second point is information contained in vertices will push subtheorem further. Which means that if we have a subtheorem which is determined by the symmetry principle to the certain order, then with the information of the fundamental vertex, we'll have a higher order symmetry. We'll have a higher order subtheorem. Or if we can derive the subtheorem purely using the 3-point or 4-point vertex, then we may have a higher order subtheorems than the subtheorems derived only using the symmetry principle. And the third, the direct output of symmetry will survive the correction. Everyone knows that we have a lot of methods to derive a subtheorem. But we can, like stage Y or else, but they are all tree-level method, and the subtheorem may be violated in the loop level. But if we derive the symmetry, if we derive the subtheorem using the symmetry method, then it will be valid in the loop level. Okay, let's get started. I'm first talking about what is a subtheorem. Okay. What is a subtheorem? A subtheorem is that if we have an amplitude and we take one of the legs to be soft, which means we take the momentum to be approaching zero, then the amplitude will be proportional to the lower point amplitude, in which the soft leg is removed. Then if we take the n+1 point amplitude, take the p to be 0, then it will be proportional to the n point amplitude, where not this p particle in it. Okay, and not every amplitude will have soft theorem, and some amplitude will have 0 soft theorem, which means if we have a n+1 point amplitude and we take p to be 0, then it should be 0. Okay. And some amplitude it have a divergence of theorem, which means that this expansion start at the order of 1 over p. Okay. But the simplest case is that we expand the subtheorem from the order of 1. So in that case, we call the S0 to be leading subtheorem, and S1 to be subleading, and S2 to be subleading, and so on. And we can take more than one leg to be soft. Okay, like we can take 2. Therefore, we have a double subtheorem. But if we take 2 legs to be soft, then to do a double expansion in the P and the other Q, then we'll have two expansion scenarios. This is if we can expand expand P first and Q later. Or we can expand P and Q simultaneously. Then we have two kinds of different double solved theorems. Okay. And the difference between the two kinds of theorems is only depend on the 4-point vertex, which may be modified by the UV correction. So this kind of double solved theorem may be violated in the loop level. The detail of the calculation is very complicated, so it will be left for the next talk of Shunqing. And let's show how can we derive solved theorem from broken symmetries. Okay, let's first see the word identity. If we have a broken symmetry, there we have a broken generator G, and by no recurrent we have a no recurrent J mu. Then, if we take derivative to the time ordering bracket, J mu of the current and n arbitrary operators, it will be equals to the summation of n parts. In each part, we have a commutator of G and the operator. And if we take the operator to be a current or a field, then it will generate a single particle state. Then we have an n plus 1 point amplitude to be related to an n point amplitude. Okay, if we have the commutator of G and the field to be proportional to the field, then there's this solved theorem, where the soft vector here is the summation of the Gi tilde. Gi tilde is the proportional vector here to be Fourier transformed. Okay. In the LC reduction here, we should do the n plus 1 times LC reduction here in the left-hand side, and n times of LC reduction in the right-hand side. So, but we have to do the same thing in both sides of the equation. So we will have the momentum of the current J to be solved. Then we can have two momentum here. The J mu generates one P and particle action and another P. So we'll have a valid LC reduction. Then it forces the momentum of J to be 0. So it's a solved theorem. For example, we derive the double solved theorem from this method for DBI, where this is the leading part, and that is the subleading part. And in principle, we can derive the sub-subleading part. For conformal DBI, the leading and subleading part is derived by this method. And for the AB model, which is the model of Gaussianus of the broken supersymmetric, this method can derive the double solved theorem to only the leading part. Okay. But how does the vertex contribute to the solved theorem? Okay, let's see this diagram. This is the famous Weinberg solved theorem. If we have a momentum, a leg of momentum P here, then this diagram is like this form. Here we have a vertex and a propagator here. Then in the leading piece, there should be a solved theorem. But the right diagram only contributes to the subleading part, and it looks like it's not proportional to an n-point amplitude. So how will we get the solved theorem in the subleading order? That is for the theory that have some gauge symmetry or there are some gauge symmetry like photon over graviton. Then the gauge symmetry forced the two diagrams to be proportional. So in the subleading order, the two diagrams sum into the form that is proportional to the left diagram. So it's proportional to the endpoint and the 2. So 3-point vertex here with the gauge symmetry will give us the soft theorem to the subleading order. Another case is that in the double soft case. I mentioned that the two kinds of double soft expansion will differ only by this diagram. Okay, and this diagram will, and this difference will only concern of this vertex. That is a 4-point vertex. So if we have 4-point vertex, we can derive the double soft from two single soft diagrams, two single soft theorems, which is symmetry protected, and this vertex, which is not protected. Let's see how it is true. It's the double soft theorem of DBI, which is derived by the CHY formula in their original paper. The CHY formula is known to be as a tree-level technique that may not hold in the loop level, but only the sub-leading piece of sub-theorem to be valid. Why? Because we can use our symmetry test method to derive the leading up. Here, the leading part is 0, because we start at the subleading part, or to start at the order of tau. Here, tau is the soft momentum. We can derive the leading and subleading part, and in principle, we can derive the sub-subleading part. Use the symmetry principle. So, these two parts is protected, and this part is not protected. In our explicit test, DBI soft is embedded in the order of tau squared, tau cubed in the 4D, but it's valid in 6D. Why? The reason is that the loop correction only introduced a vertex which is in the order of tau 4 in the 6D. So it's valid in 6D that in the order of tau cubed. And we derive the couple DBI and the AFP model in the symmetry test method, so they are all true. But in the string case, things get interesting. In the alpha prime expansion, we have the STU, which corresponding to the order of tau squared. It's potentially can modify the soft theorem, but it holds true because we can derive it from the symmetry principle. Okay, so today's conclusion is that soft theorems derived by any method holds true if it can be derived by a symmetry-based principle, a method. And what we will do is to deal with double or multiple soft theorem more systematically. Thank you for your attention.
Question? I have a question. To go to the page that you say when the soft pion attached to the middle part of the diagram.
Yeah.
Okay, that is one. So you said that the diagram on the right side is subleading.
Yes.
So could you explain why it is subleading?
Oh, because here is leading because the Ki plus P is unshared.
Right. So the
K plus P
offshore.
is offshore.
Okay,
So
yeah, that's the reason. So now you sum the right side, okay, the right side diagonal to the left hand side. So it's not clear to me because if I can imagine if the P is the photon, it's quite easy to understand.
Yeah,
we have the word identity, but for the pion, so I'm not sure how.
For the pion, the story is not like that. So the pion, we do not use this diagram, but we use the symmetry principle. We use current algebra to directly derive the sub-theorem. So even if it doesn't concern about the vertex. So for pion, the sub-theorem will hold true in the higher order.
So did you really check for example, you write down the Feynman rules and?
No, for pion we don't use this.
You don't use it, but if you use this, can you show it?
It may be very complicated. But for the pion or non-exact model, they don't have the 3-point vertex here.
Do you have a comment?
I think yes. For if you run out of Feynman rules,
It's
basically
step by step.
yeah, for single solve, for double solve. For double solve, it's what I showed with the one versus argument.
Okay, and this is the second speaker again. Thank you.